Okay, I want to talk about piecewise functions. First, what is a piecewise function? You guys know?
Nope.
Okay, don't overthink this.
It's a function they put into pieces.
Yes.
Like a composition function.
No.
So when people ask you what you do you tell them you compose functions?
No.
I'm a composer of numbers.
I tell them I teach math, and then they make some kind of cringing noise.
Oh,
That
Or yeah, it's like cool.
I see how you feel about
Thanks. So a piecewise function is a function defined in pieces. Okay? Which means you chunk the domain up into some bits, and then you maybe do different formulas for the bits. You guys know an example of this already. Do you want a default example? Okay.
The prototypical.
The prototypical example is a of x is absolute value of x.
Okay. So
How do you do the absolute value of x to stuff?
you just take its
Plug in the
numerical
values and-
value.
Kinda. Yeah, say that thing again. Make it positive is the
fair.
way you guys use. That's the way students usually think about this, right? This is the function that like makes x positive.
It's distance from 0, right?
Yeah, so if you wanted a good definition, distance from 0 is a nice, easy definition. But that means that you treat two things, like you chunk the real numbers up into two categories of objects and you treat them differently, right? What are the two categories of objects and how do you treat them?
Negative and positive. They're both treated positively.
Okay, so if a number is positive, right?
Yeah.
And this is the piecewise thing, right? I'm making a bracket here and I'm going to put the pieces in here.
Okay.
So I'm going to say if x is bigger than or equal to 0. So if x is positive, right? If you're feeding a positive number in here, what do you do with it?
You just, that's it. That's the answer.
Yeah, nothing. You just leave it alone. Right? So it just returns the input you gave it if the number was already positive.
Yeah. So for negative numbers, you multiply by -1.
Nice. So if x is less than 0, you do minus x. Right? You just slap another negative sign on it, and that makes it
Positive.
positive. You guys with this? So why doesn't this part make negative numbers out of this thing?
Because, wait, what?
Like this is making things negative, right?
No,
I thought it was
only
supposed to
if it's
make it
already
positive.
negative.
Okay, good. It was already negative, right? And the only way to get to that part, right, is to have something that's already negative. You guys with me on that?
Yeah.
Okay, I'm going to give you another example just to illustrate something kind of weird that can happen. This is a classic for engineers. This is called a Heaviside function. Okay, anybody know Heaviside? No? Okay. The Heaviside function is a light switch. So, it's divided into two pieces. The pieces are, again, positive and negative. Okay. So, if t is bigger than or equal to 0, this thing's going to return 1. And if t is smaller than 0, this is going to return 0. Very nice. You guys with me on this? So the thing I wanted to illustrate is the graph here. So if that's the t-axis, and that's the whatever axis,
Heaviside axis.
So, when t,
so what does this thing look like?
so anything to the left of I, the
So anything left of
Any
the kind
negative
of
t's.
output axis,
Any
right,
negative t's
gives you
up 0. So you're just not
0. So you're right here.
Yeah, you're right on that line. anything to the right of the origin on the x-axis gives you a 1 on the y-axis. So just a line,
Like this?
just like that.
Okay. I think I need some circly dot
Hollow
things.
circle on the
Hollow circle where?
the T, H of T or
On
whatever.
the y-axis.
Yeah.
Right here?
So nothing happens at that because it doesn't exist.
Well, where does 0 go?
It's like
Well,
the middle. Oh, 1.
You know, closed circle on the.
Yeah, 0 is, so when you're plugging a point in, right? When you're plugging a t value in, you need to go to the piece for that value.
Okay.
So if I try to plug 0 in, is 0 bigger than or equal to 0, or is 0 smaller than 0?
0 is bigger than or equal to.
0 is equal to 0, so it fits in the bigger than or equal to part. And then what's my output?
1.
1. So there's actually a closed dot up here at 1,
Okay.
and an open dot down here at 0. You guys see that?
Uh-huh.
So what I want to illustrate with piecewise functions is they can do this kind of funny jumpy thing.
Okay.
You guys all with me on that?
Yeah.
Okay. This function is specifically not what? What's the word for what this function isn't?
Linear?
Good, it's not linear. It's also not. It is a function because it passes the
It's not an even
Vertical line test.
vertical line test, so it is a function. The word I'm looking for starts with a C.
Constant.
It's a different word that starts. And also, this function is not constant, right? Even though it's flat everywhere.
It's not connected.
Yeah, close. Continuous. This is a discontinuous function, right? This category of thing, right? Where this guy kind of jumps, right?
Yeah.
Creatively enough, is a jump discontinuity,
Of course it is.
right? Because of course it is. What else would you call it? It's clearly a jump.
Jump discontinuity.
You guys cool with that? So there's a couple kinds of discontinuities. A jump discontinuity is kind of the classic one that happens with piecewise functions. Another one that's possible is, you guys know another kind of discontinuity?
Asymptotic.
Yeah, asymptotes are another one. Well, we'll get to playing with continuity some more later. Right now I just want to highlight that this business can happen. So you might have a piecewise function that has a bunch of jumps in it. That's totally okay.
So with the absolute value function, is the jump to an extent where it meets at the v? Like,
Let's look at the graph. What's the absolute value function look like?
A V at the origin.
Yeah, it looks like a V with a kind of vertex at the origin, right? You might notice that this is the right half of the line y equals x, and this is the left half of the line y equals minus x. You guys see that? Like, oh yeah, duh. Like, that's the pieces it's made out of, so duh.
Yeah.
You guys kind of with me?
Yes, it's very.
Okay, so is there a jump discontinuity here?
No.
No.
No, it's continuous there. So it's possible, right, if the pieces meet at the ends, that you could have a continuous function. It's also possible that you might have a jump discontinuity if the pieces don't meet. Is cool with that?
Yeah.
Okay. I'll do this. I'll just do an easy version. I'm going to call this a P of t for pop function.
Pop.
Yeah. So,
Is that soda thing?
what? No, not soda. Pop. Okay. One thing you might think about, if you're gonna be some flavor of engineering, you want to go look at a cool thing. This is modeled a little bit on something called the Dirac delta function, which is not a real valued function. It's what's called an extended real valued function. It's kind of a cool thing. Okay, so I'm just modeling this a little bit, but I don't want to introduce another category of function, so I'm just going to make this little pop function. And the pop function is going to have 3 parts.
Whoa.
Okay, and they're going to be 0 if t is smaller than 0, and 0 if t is bigger than 0.
What happens if t is 0?
And at t is 0, I'm going to put in 1. You guys with me on this?
Mm-hmm.
Is this the best way I could have written this?
Why do you ask? I mean, it's a fine way of writing it.
Okay. Is this really 3 pieces? How about that?
No, it's just all, no. It's just 0 except for 0.
Yeah, this is really just 2 pieces, right? Like another way to write this would be to say,
Always 0 except up.
this is 0 if t is not 0,
And 1.
right? And 1 if t is 0. You guys with me on that?
Mm-hmm.
Okay. What does this thing look like?
That looks like
A dot.
a dot in the center.
There's an open dot at the origin and a closed dot right above it.
Okay, cool. So it's 0 except at the origin,
Yeah.
and then at 0,
It's fun.
there's a dot up here at 1. You guys see that? That's kind of a special sort of jump discontinuity, right?
Mm-hmm.
You guys see that? It jumps up just the one time, like at one very lone point. You guys cool with that? Okay. The Dirac delta function is similar. But, things you might model with this are like if you hit something with a hammer, right? This would be like the force transferred, right? Like there's no force, and then bam, and then there's no force.
Oh, so it's over time.
Yeah.
Okay, that makes so much sense.
Whereas this heavy side function, what's that good for?
Light switches.
Yeah, like a light switch, right? You're turning the light switch is off until you turn it on at time 0, and then it's on. You guys see that?
Yeah.